All right, it's time. You have one announcement to make. Our second exam, everybody should have their first exam back now. Although I haven't sent the extra credit back, which is added to your score. But exam 2 is actually in 9 days on Thursday of next week. So I'll just remind you of that. On this Thursday, I want to put out a list of review problems so look for review problems in 2 days. On Thursday. Practice test like the last one. Make sure you can do all those for the test and the homework problems besides. Today we want to do some more with inverse trig functions. I want to sort of summarize what we've been doing and add a little bit more to it so you feel like you're more capable of solving more problems. Then we'll talk a little bit about identities today. So we said the following concepts. I just want to
would you mind?
One,
if you're available, would you mind shifting the camera to the side? It's not covering me.
An inverse trig function when the result is a special angle.
The camera isn't covering that.
You hear a voice on there? Maybe I have the sound down too low. Good. So there's that. I think it's way turned down. Okay, I've got the sound up. If anybody was trying to say anything, go ahead and speak.
You might want to shift the camera to the side. I can't see that. I can only barely see the right end. Okay. I can only barely see the right end of that.
Yeah, I had this in a different position. I forgot to move it when class started. Here we go. Thank you.
You're welcome.
So exam 2 is a week from Thursday. Review problems coming out Tuesday. Today we'll continue inverse trig. And the first comment is whenever you're taking an inverse trig function of a number that comes from a special angle, you can do it exactly. So here's an example just to extend what we did last time, a little harder. What is the inverse secant of minus the square root of 2? How about that? How do we do that one? A lot of calculators will do this, by the way, exactly also, but they don't usually have an inverse secant button. What you can do on these is say, well, let's let inverse secant be theta, right? Then what we want is for secant theta to be equal to minus square root 2. Then you also bear in mind that you know the range of the secant. Yes? If you plot the secant function, let's say theta versus secant theta, it looks something like this. It always gives you an angle between 0 and pi, not equal to pi over 2. So this is pi up here. And so what you want actually is secant theta equals minus square root 2 and theta in the range of the arc secant function, theta between 0 and pi over 2, or pi over 2 and pi. In other words, the first or second quadrant. That's a hard problem to solve with secant, but if you turn this to the reciprocal and say, oh, this is just by taking the reciprocal of each side, cosine theta equals minus 1 over square root 2, with theta in the first or second quadrant. Then we can solve this in the unit circle. So all these boil down to is solving them on a unit circle and looking for the right quadrant. But if it's arc secant, arc cosecant, or arc tangent, you turn it into the problem with the reciprocal function. So here's cosine, and I want cosine to be the x coordinate. So I want x equal minus 1 over square root 2, that's about here. And that means there's two terminal rays, one right here, one goes through right here, and one goes through right here. There's only two terminal rays that can give you the x coordinate equal minus 1 over square root 2. These are all the points in the plane where the x coordinate is minus 1 over square root 2. That's the unit circle like that. And so which one is it? Well, it comes by the quadrant, the inverse secant, and actually also the inverse cosine. Give you something that's in the first or second quadrant, and so you throw out this one saying that's the wrong quadrant, it must be this one. And now if this is minus 1 over square root 2 coordinate, then the length of this side is plus 1 over square root 2. This side is 1 because it's a unit circle. Now I recognize the triangle. If I don't, I use the Pythagorean theorem to find the left side. But 1 over square root 2, you always need to bear in mind in this class, is the same as square root 2 over 2. And now maybe I recognize the triangle. It's a square root 2 over 2, square root 2 over 2, 1 triangle. This is a 45-degree angle, which we'll label as pi over 4 because almost all of these inverse trig functions we want to do in radians rather than degrees. The reason being that more applications in mathematics are for radians. Although there are plenty of applications in degrees also in other fields. Okay, so now if that's pi over 4, the angle I want is the angle in standard position. This angle must be pi, a straight angle, back up to pi over 4. In other words, these two have to add up to pi. So this one must be 3 pi over 4. There it is. The inverse secant of minus the square root 2. 3 dots means therefore in mathematics. Therefore, the inverse secant, which was theta, of minus square root 2 is just 3 pi over 4. So that's the hardest they get, is you can put them in a difficult quadrant and ask for an inverse secant, inverse cosecant, or inverse cotangent. All right, secondly, the kind of thing you can do, and once you be able to do this for the next test, there'll probably be something like that on there. The second one you can do is a trig function of an inverse trig function can always be evaluated exactly. Doesn't matter if it's a special angle. So we talked about this briefly at the end last time. I want to do at least one more. And here's what you do. It's that 3-step method. Step 1, let's call it A this time because I'm using 1 for the numbering of 1, 2, 3 for the numbering of the topics. A, you draw a right triangle with the inverse trig function you see. Right? So if I put theta here, what I want, oops, I forgot to put the problem on here. So problem A is, suppose I have the arc tangent oh, there it is. That's right. The cosine of the arc sine of x over x plus 1. This doesn't have to be a special angle, right? After all, x is arbitrary. So I can do this for any angle in here. We did one at the end last time like that. What can I do with this one? One, you make the right triangle. So this is the example, and I guess I should have called this A. With the theta equal the inverse trig function you see. So you let theta equal, in this case, arc sine x over x plus 1. Now in a right triangle, that implies that the sine of theta is this number, right? Why is that always true? That if you're in a triangle, theta equals the arc sine means that sine theta is this number here that was in the arc sine. It's because in a right triangle, since this takes up 90 degrees, these two angles add up to 90 degrees, so they're each less than 90 degrees. They're in the first quadrant. Angles in the first quadrant, the inverse trig functions are always undone by the trig function, right? The sine undoes the arc sine in the first and fourth quadrants. Cosine undoes the inverse cosine in the first and second quadrants. And I wrote that backwards, but the inverse sine undoes the sine in the first and fourth quadrants. The inverse cosine undoes the cosine in the first two quadrants. But every inverse trig function undoes the trig function in the first quadrant. So as long as we're in the first quadrant, sine theta equals this is the same as theta equals the arc sine of this. So we'll do that. And now if sine theta equals that, then I can write a ratio of opposite to hypotenuse that it looks like this. So let's put x here, and x plus 1 is the simplest way. I can put 2x and 2x plus 2. Who wants to make it harder, right? So I make these two sides in this ratio, opposite to hypotenuse. Now the second step, B, is to apply the Pythagorean theorem to get the last side. So the last side here, since it's a leg, is going to be the square root of the hypotenuse squared minus the leg squared. Now be careful on this, because what a lot of people do on this one, you see this on your ACT exam, for instance, is they'll say, oh, that's x squared plus 1 squared minus x squared, and then cancel the x squared. What's wrong?
It's squaring the whole thing as x plus 1 has its own.
Yeah, I need to FOIL it out. I'm squaring the whole thing here. If I think about it, x plus 1 squared is not x squared plus 1 squared. It's x plus 1 times x plus 1 is x times, you FOIL. This times this first, outside, inside, last. X squared plus x is 2x plus 1 times 1. So you take all possible pairs, these two, these two, these two, and these two. And you get this. And so this comes up x squared plus 2x plus 1 minus x squared. And now these cancel. And we wind up with square root 2x plus 1 on the last side. There it is. Now step C, you use the triangle that you have to evaluate the original expression. So you say the cosine of the arc sine of x over x plus 1 is equal to the cosine of theta, because I built theta that way. But the cosine is the adjacent side over the hypotenuse, is 2x plus 1. That's the square root 2x plus 1 over the hypotenuse x plus 1. There we go, exactly the cosine of the arc sine for whatever x is. How about that? Amazingly, these trig functions of inverse trig functions always come out to be algebraic expressions of the original number there. All right, that's number 2. Then number 3.
Yeah, I didn't get the last. One.
Let's leave that for a minute.
Okay. Thank you.
Yeah. Number 3, we want to be able to calculate an inverse trig function of a trig function. We can also use the unit circle. See how useful it is? So inverse trig, this will be the other order of the same trig function. Can also use a unit circle. Remember what we had before? We said, for instance, we'll just do this by example. If I take the arc sine of the sine of x, I'd like to think that's x because they're supposed to be inverse functions, but we only inverted a piece of the sine function. So it only would works for that piece, which was minus pi over 2 less than or equal to x less than or equal to pi over 2. And we get something else otherwise. What is that something else? There's actually a nice formula if you happen to be in the second quadrant, for instance. Let me just do this by example here then. Let's say the inverse sine of the sine of 5 pi over 6. What if I wanted to do that one? I can sketch the 5 pi over 6. Well, pi would be a straight angle. This is 5/6 of pi, so it's almost a straight angle, right? 5/6 of a straight angle. That leaves 1/6 of a straight angle, right? So these two add together to pi. Now I can drop the perpendicular and I can compute exactly, since this is a special angle, 30 degrees, the sides here. This side is a half, this side is square root 3 over 2. Evidently the coordinates are minus square root 3 over 2 plus a half. And I observe that sine is the y coordinate, so now what I have is that the inverse sine of the sine of 5 pi over 6 is the inverse sine of a half. What's the inverse sine of a half? I can do that on the unit circle too. Let me use a different color here. To solve the inverse sine of a half, I'm asking what theta between minus pi over 2 and pi over 2, the range of arc sine, has sine equal this number. That's how you solve this. And so I take the y coordinate equal a half, and I say, oh, wait a minute, it's the angle I just had, maybe. There's one point in the unit circle, but there's another one right over here. And what we want is the angle between plus and minus 90 degrees. It has to be first or fourth quadrant, so it has to be this one, actually, not the original angle. Now, if this side is a half here, that makes this side a half here. And in fact, by symmetry, since this is pi over 6 this way, this is also pi over 6 this way. So the correct output here is the angle in the first quadrant that has the same sign, pi over 6. Now, the arc sine of the sine of 5 pi over 6 is not 5 pi over 6, right? It's something else. It's pi over 6. And here's how you can think about it. It's the angle in the first or fourth quadrant that has the same sign as this angle. That's what we calculate. I'll do one more to emphasize that. But what we did was we found the sine of 5 pi over 6 in this example. And then we needed the same y coordinates. We found the angle in the first or fourth quadrant that had the same sign. So that's what this is really asking when you take an inverse trig function of the same trig function of any angle. Here's how you can calculate it more generally. Hopefully I have enough time to write it down. This is a useful result here. We'll say that similarly, for any theta in quadrant 2, here's what we have, the inverse sine of the sine of theta. What could it be? Here's my angle, say. And then, oh, yeah, okay. And then the sine of theta is the y coordinate here, right? So there's the sine of theta. Is y. We want the inverse sine that has the same y coordinate, right? This is y. So and this is asking what angle phi, let's say, for the other angle, between minus pi over 2 and pi over 2. Oh, I should, let's see, yeah. Has this y coordinate. I call this y, the same y coordinate. Well, it has to be an angle between here and here with the same y coordinate, just like in the last example. So it's got to be that angle right there. Well, what angle is that? For the second quadrant, we notice if this is theta, this angle must be pi back up theta, right? That pi minus this one leaves this one. Well, then by symmetry, since this goes up to the same height, this angle must be the same one. I turned it counterclockwise, I'll turn this one counterclockwise. This is also pi minus theta. That's your angle phi that has the same sign as the original angle. So the answer is that this is always pi minus theta in quadrant 2. So for example, now I could say, what is the inverse sine of the sine of 9 pi over 10? Oh boy, it's not the right, I can't just say it's 9 pi over 2 because this isn't between, right, it's not in the first or fourth quadrant, it's not between minus pi over 2 and pi over 2. So what is it? According to this, it says pi minus whatever the angle was. It's pi minus 9 pi over 10. Since this is in quadrant 2, I'll say it's pi minus 9 pi over 10. It's actually just pi over 10. Similarly, you can do this in other quadrants. So similar result in other quadrants. But what that shows then is you can take the inverse trig function, the same inverse trig function of a trig function of non-special angles, and find the exact result just by subtracting it from pi. Okay. And then you can do the same with cosine. And tangent. Suppose I want the, let's do this in, we have the cosine, inverse cosine of the cosine of an angle theta, x, let's say, was equal to x if x was in quadrants 1 or 2, right? So 0 less than or equal to x less than or equal to pi, that's the piece of the cosine function that we flip to get the inverse cosine. And it gives you something else otherwise. I wonder what that could be. Turns out that you can do a similar result. By the unit circle, suppose, say, for instance, I'm in a different quadrant, I'm in quadrant 4, and here's my And maybe I better use theta again. Here's my theta down in quadrant 4, and I want to know what angle, what is the arc cosine of the cosine of theta if I'm not in quadrants 1 or 2, but down in here. Well, this is the x coordinate this time. And you observe that the angle on the unit circle, and you're asking what, and when you say the result is the same, the angle in quadrants 1 or 2 with the same cosine, right? You take cosine theta is equal x, some number, and then you say arc cosine of x is the angle in quadrants 1 or 2 that has x as its cosine. But x was the cosine of this one, so you're asking for the angle in quadrant 1 or quadrant 2 with the same cosine as theta. So I look and say, well, if I drop a perpendicular here, this x coordinate is the cosine of theta, right? What other angle can I get but in quadrants 1 or 2 to get that cosine? It has to be this one right here. Well, what angle is that? In order to drop to the same position, I have to turn through the same angle here. This has to be theta if this is theta, which means this one is just actually minus theta. Right? It's the same turn, but the opposite direction. So evidently, this is actually just equal to minus theta. So the inverse cosine of the cosine theta is actually minus theta. And what we have overall then is that the arc sine of the sine of theta comes out to be pi minus theta. Actually in both quadrants 2 or 3. And then the inverse cosine of the cosine of theta just comes out to be minus theta. Theta in quadrants 3 or 4, the two that you can't get to with the arc cosine normally. Then if you have angles too large or too small, you can look at it similarly in the unit circle. If you have multiple rotations or something like that. Okay, so there's another one you can do exactly. And then there's some applications. I wanted to make sure I did some applications. So step 4 is to say that triangle applications usually require a calculator because you don't get a special angle out.
If you wouldn't mind shifting it to the...
Yeah, thank you. Because an inverse trig function of a non-special angle is needed. Let's say when. Inverse trig function. Inverse trig function of a non-special angle occurs. Here's an example out of the homework. Suppose I said, I want to find the angle between the line from algebra y equals minus 3/7 x and the negative x-axis. To me, this question is not explicit enough. I think they should add a little more and say, measured positively, no matter which way you turn. How would I do that? On applied problems, always draw a picture. If it has geometry. So we'll draw this picture. What does this line look like? This is where you have to remember some algebra. Y equals minus 3/7 x. How do I even know it's a line? What you do is you think of this as minus 3/7 x plus 0, and you say this is in the form y equals mx plus b. So m must be the slope and b must be the y-intercept. And it shows that it goes through the origin, right? If the y-intercept is 0, then you're going through the point 0, 0. So it goes through here, and then minus 3/7 is the slope. So we can make this the rise, which is now a fall, really, because it's negative. And this can be taken as the run. So we'll go down 3, 1, 2, 3, and over 7, 1, 2, 3, 4, 5, 6, 7. And the line goes through that point, right? If it starts here, it can go down 3 and over 7, and that's a slope of minus 3/7. Now the question is, what's the angle between this line, which goes up in this direction too, and the negative x-axis, this angle right here? Well, look, if this is 7 units, run, and minus 3 rise. Then over here, we can also do a minus 3 rise and a run of 7, right? And we can say for side lengths that this is a 3/7 triangle. And also over here. And therefore, what's this angle? Once you draw the triangle, it's obvious. We notice that the tangent of theta, this angle of the triangle, is 3/7, right? Opposite over adjacent. And for triangles, we always call the angles positive because there's no need for right triangles. That is, well, all triangles. We don't need to make negative angles in triangles. So we'll say tangent theta equals 3/7, and theta is in quadrant 1, right? This is an acute angle. So we know immediately that theta is the inverse tangent of 3/7 just because it's a right triangle. Well, let's run that on the calculator then. I just remind you then, for calculator, you put second or FCN or third, it depends on the calculator, usually second. 10, because up above 10 is inverse tan or arctan. And so in the same color as the key, and so you push blue key to enable the blue instruction arctangent. The calculator automatically inserts 1 or 2 parentheses. Let's assume it inserts 2. Then I just need to put 3 divided by 7. Maybe I close the parenthesis depending on the calculator, and then I push enter to evaluate it. That's still on here? Okay. And so on this one I get 23.19. Wait a minute, isn't that an awful lot of radians? What's going on? And there's more to that. That's 1985 actually. The calculator is in degrees mode. If the calculator is in degrees mode, then it will output the arctangent in degrees. If I switch my calculator over to radians mode, let's do that. Mode, then to radians. Then I'll do the same thing, arctangent 3 divided by 7. Now I got 0.40489. And a bunch of other stuff. Or approximately 0.41, the answer that's on the back of the, this is a problem out of the homework. This is the answer that's in the back, about 0.41 radians. So the answer you got from doing these on the calculator will depend on what mode your calculator's in. Well, that's all I wanted to do on inverse trig functions. I think that runs the gamut of it. But the last thing we want to do is coming up, we're going to solve equations involving using inverse trig functions. That'll come up after we do a little more material. So for the rest of today, what we want to look at is trig identities. This will be the next section. This will be on the test Thursday of next week, and however else far we get this week. There are two main purposes we study the identities. There are other purposes to be sure, but we use these a lot in practice to simplify trig expressions. This is really useful in a lot of the sciences. It's very common, you come out at the end of an experiment or something, you say the output is this, y equals 2 sine squared, let's say 2 cosine squared theta, plus 2 sine squared theta. I say, I wonder what the graph of that wave looks like. It's pretty complicated, right? After all, if I look at 2 cosine theta, 2 cosine theta looks kind of like this, right? Goes up and down between plus and minus 2. And I said, well, what does 2 cosine squared look like? Well, the square of cosine is always non-negative, right? Because it's square negative number, you get a positive. And so it looks something like this. If you were to plot it, it goes up to when cosine is 1, 2 cosine squared is also equal to 2 like this. And so you get something that looks more like that. And then here it goes up as the square of this negative, and it goes like this. And so if you plot it, you can plot it on your calculator, right? The graphing calculator lets you plot this. It looks something like that. That's 2 cosine squared is the blue one. And then over here, I might say, well, what does 2 sine squared look like? Here's sine theta times 2. And its square is non-negative. Whenever sine's equal to 1, then 2 sine squared is equal to 2 sine. So it will look something like this. Here's, let's go up to 2. Here's y equals 2 sine squared theta. And boy, I have to do a lot of thinking to it. Now I have to add these two together. I wonder what they add together to look like. Anybody figure it out? What does it look like when you add them together? Here's theta again, theta versus y, theta versus y, theta versus y. And now I'm going to plot y equals 2 cosine squared theta, this one, plus 2 sine squared theta, this one. What should it look like? Here's where the trig identity shines. You pull out the 2. It's 2 times sine squared plus cosine squared, right? I can add in either order. this times this is this term, right? This times this is this term, right? So you're just saying A times B plus A times C is by the distributive property the same as this. But now sine squared plus cosine squared is 1, so this is 2 times 1. Remember the Pythagorean identity? One of the more important ones of the semester. This is just the constant function too. If you write these just right, they always add together to make 2, excuse me. And so what the graph of the sum of those put together is just the straight line, horizontal line, y equals 2. That is what this is. All I needed was a trig identity to recognize, actually, it's only a horizontal line. The chemical reaction or something is constant. So this is what comes up in practice is you get these kind of things out of some theoretical result, and then you can simplify it. It really makes your understanding of the function a lot easier. So that's just an example sort of to get us going. I want to remind you of all the identities we've done so far, and this first section then is going to be on using these identities we've already been looking at to try and simplify expressions and to solve this equation. So we'll write this general strategy that I'll call rules of thumb for simplifying. And these aren't absolute rules. A lot of times you'll find something that's faster. You're welcome to use any true results, right? Just don't use big ones. Rules of thumb for simplifying. And these will work on all your homework problems. This is what everybody does, even though there are certainly more ways to simplify than this. One, you use algebra. What happens a lot of times, because you have quotient identities and so forth, is you get quotients and you get quotients of quotients. And so what happens is you combine sums or differences of quotients by putting over a common denominator. Just like you do in algebra, it's just now they're quotients of trig functions. So you can combine quotients by making a common denominator. What if you have a quotient of quotients, like 2/3 over 4/27? Well, you take top times bottom over middle times middle, and then you cancel common factors, right? There are some in there. So you also eliminate compound quotients, and you cancel common factors. This is not an exhaustive list of algebra. These are common algebra things that you do. So I'll just get you thinking about these. And this will greatly simplify your trig expressions. All right. So algebra is the first thing you try to see if you can reduce it that way. Now, if you're stuck on that one, you don't see anything to do. Then you apply a trig identity. Like in this one, that's all we did. Well, we did a little algebra, first to factor out a 2 and rewrite this in another order. So that was algebra. And then the next step, once we did our algebra, we applied a trig identity, simplified it immensely. That's step 2. And then 3, if you're stuck, a real good strategy that works quite often is to try rewriting everything in terms of just sine and cosine. If you've got 5 different trig functions in there, it's really hard to see an identity, but often if you rewrite it with just these 2, you'll see sine squared plus cosine squared somewhere. Aha! You know, and so you can reduce it. So try rewriting in terms of sine and cosine only. This just takes practice to go through these things and do a bunch of problems. You just, you know, it's like learning a sport. You just have to try it until you get quicker at it. Okay. And then I'm gonna add one more of these, but I'll put it at the top. We don't really need it so much yet. But in the next section, when we start introducing new identities, besides the ones we have, we're gonna have some that have multiple angles. We have 2 theta here and 4 theta there and 1 theta here, and you wanna combine them to get one angle. So we'll say tacitly assume in here before we start that we get one angle in all the trig functions. Don't have sine of theta in one place and sine of 3 theta in another, for instance. So that's it. That's my strategy. It's not written exactly like that in the book, but they do the same things. And there's some really nice examples here. This first one will be simple, and then we'll work up some harder ones and see how you get. What you do is you do this actually as an iterative process where you start here and you go through these steps, and when you're done, you go back to the top and try them again, and go back to the top and try them again. And you repeat this until it's simplified as far as it goes. And then before I do the example, I need to list the trig identities. We have so far these trig identities to apply in step 2. We have the Pythagorean identities. And so in this section, they're just going to have, it's nice to have this list in front of you and say, can I apply this? Can I apply that? And that gets you used to thinking about it. Pythagorean identities are this one. This is the most important one. Sine squared plus cosine squared equals 1. What's another one? All right, get another Pythagorean identity. This one comes out of, here was the proof. I just want to remind you in case you forget it. If you take an angle theta, it works in other quadrants, but it's easiest to see it in the first. Then the y-coordinate is sine theta, and the x-coordinate is cosine theta. And the hypotenuse is 1 because it's a unit circle, right? So here was the proof. This squared plus this squared equals this squared by the Pythagorean theorem. Aha! No wonder it's called the Pythagorean identity. It's proved by the Pythagorean theorem, right? So you prove this one on the unit circle. And that makes a nice, easy way to remember it if you forget. Now the other ones follow easily. You divide this through by cosine squared, what do you get? If I divide the left and right both by cosine squared, then I have to divide each term by cosine squared. Sine squared over cosine squared is what? How about that? I divide this through by cosine squared. I'll erase this in a second. If I divide the whole thing by the same number, then it's still true. Sine over cosine is tangent, and if I square both of them, it's tangent squared. Right? This one, you can put the square on the outside, and it's tangent squared, right? Same thing here. You can put the square on the outside, and it's 1 squared. So tangent squared becomes this divided by cosine squared. 1 becomes this divided by cosine squared, and then 1 over cosine squared is 1 over cosine quantity squared is secant squared. So that's how you prove the second Pythagorean identity. Just divide the first one through by secant squared. When I was a trig student a long time ago, I had trouble remembering these last two. They were harder, but I could divide them through and figure them out, right? You have to remember, which side is the 1 on? I can't remember. You just divide this one through. This is the easy one. Now, if instead you divide this through by sine squared, then sine squared over sine squared is 1. Cosine squared over sine squared is cosine over sine squared, or cotangent squared. And 1 over sine squared is cosecant squared. There are the Pythagorean identities. You have to know these when you get out of the class. They're used all the time in higher courses. If you don't memorize these, you can figure them out, right? From the first one. So that's some very important identities. How about these, the quotient identities? Remember those? The quotient identities, where there's 2 of them, you said tangent theta can actually be written as sine over cosine theta. And similarly, cotangent theta is cosine over sine. These are used extensively. Have to memorize those. Now you can see what's happening. It's like learning a sport with soccer or something where you got to be able to kick it this way with the side of your foot, and you gotta lift it up on your toe another time. So you got all these different moves and you gotta coordinate them. Is the trouble, right? So now 3, we have the reciprocal identity. Remember those? We recall that cosecant is 1 over sine, right? It's the reciprocal of sine. We've been doing these trig functions. We write the first 3 and then do 3 reciprocals usually. The second one we did with secant was the reciprocal of cosine. And cotangent was the reciprocal of tangent. And then if 2 numbers are reciprocals, they're reciprocals of each other. So it's also true where everything's defined that sine theta is 1 over cosecant theta, that cosine is 1 over secant, and tangent is 1 over cotangent. Far enough over, maybe not. I guess I am, right. Yeah. 1 over cotangent. There are the 6 reciprocal identities. It's nice to have a list in front of you while you do this section. You can look it up and, oh yeah. You know, when you're looking at the equation and then you look at this, you can see the similarities really help. Finally, these are the least important, but you still memorize them. Actually, there's 2 more here. The cofunction identities. But these last sets are not used as much in the proofs here. I say proofs. This is actually the hardest part of the book because it involves proofs. We're going to be simplifying expressions and solving equations and so forth. And I think it's the hardest material, really. So you want to practice these. Cofunction identities say this. Each trig function and its cofunction have the following relation. Cosine of theta is its cofunction sine of 90 degrees minus theta. I'll write it in radians as pi over 2 minus theta. All right. Also, it goes in reverse. The sine of theta is the cosine of theta subtracted from pi over 2. All right. Similarly, tangent and cotangent. Cotangent of theta is the cofunction of theta, so it's tangent of pi over 2 minus theta. And in the reverse, tangent of theta is cotangent of pi over 2 minus theta. So it goes both ways. Cosecant theta is the secant at pi over 2 minus theta. And correspondingly, the secant is the cosecant at pi over 2 minus theta. So there's these that you want to memorize, the cofunction identities. And then finally, I can write these over on the side a little bit. These are used seldom, but they do occur just a little. The even and odd identities. And these are the ones we've done so far then. And we'll be getting a whole bunch of others as we go along here. Every trig function is either even or odd. 2 of them are even and 4 of them are odd. What's a good way to keep track of which ones are even, which ones are odd? You can figure it out on the unit circle if you need to. That's more work than you need. Anybody got a good rule that you like?
Well, there's only 2 that are even, right?
Yeah.
So everything else is odd.
Yeah, that's what I like to remember is the cosine and its reciprocal, the secant, are the even ones. All the rest of them are odd. You think 3 must be even, 3 must be odd. Like half the numbers are odd, half the numbers are even. No. Cosine and its reciprocal secant are even. So cosine of minus theta, the minus goes away. It's an even function. Secant of minus theta, the minus goes away. It's secant of plus theta. All the other functions are odd, the minus comes out. Sine of minus theta, the minus comes out, you get minus sine of theta. Tangent of minus theta, the minus comes out, you get minus tangent. Cosecant of minus theta, the minus comes out, you get minus cosecant. And secant, cotangent of minus theta is minus cotangent theta. So there's the even odd identities. You want to memorize those. Those are not used nearly as much, though. They were more important for your graphs. Now, finally, we can do some problems. How about that? In the last part of the lecture today, which is really what you want to be about, is the idea now is you take those rules of thumb, and I'll go back there, bring those up again, and just go through them in order. Oh, I erased them, didn't I? Good, okay. Murphy's Law. Always erase what you need. So here's the first example, and this is the easy one I started to mention before. Suppose I simplify this trig expression, just like over here we simplified the sine squared plus 2 sine squared plus 2 cosine squared was real easy. This one simplifies nicely. Sine theta times cosine theta times secant theta. Maybe I can write that simpler. I wonder what that graph looks like. Who knows, right? It's a wave times something that's not even a wave. What a mess trying to figure out what that looks like, but it's actually quite easy. What should I do? I'll apply the first rule of thumb first that I unfortunately erased. I'll try some algebra. I don't see any algebra because there's no quotients yet, right? So I don't see anything where I can combine quotients or cancel things in quotients or get rid of compound quotients kind of thing. You can also multiply out. It's not exhaustive, that list there, but there's no algebra to do. So I'll go to step 2 and say, maybe there's a trig identity. That doesn't look like any of these. I have those sitting in front of me. So I'm going to go to the third step, all the way to the third step, and say, let's write the whole thing in terms of sine and cosine. Instead of having 3 different functions, I'll only have 2. I'll say this is equal to sine theta, cosine theta, and secant I'll rewrite as 1 over cosine theta. All right? Now I see it. I go back to step 1, algebra. Right? A number times its reciprocal, right? 2 times a half is 1. Similarly, cosine theta times its reciprocal is 1. So these cancel, right? And what I have is just sine theta. This, what looks like a big mess, is actually just this wave that looks like this. I can plot it easily now. And I have a full understanding that it's a wave that has a period of 2 pi and all that sort of nice stuff. So there's a nice simplification of the real easy one. You want to recognize those immediately once you've been practicing for a while. You say, oh, reciprocals, and it's canceled right away. Right? Now we'll try a harder one, though. Sometimes you have to iterate through that loop and do these things recursively, as they say. I like these problems that are in here. I'll do some of these, and you can try them at home if you get stuck. Maybe you can do the same thing as some of these. So I'll call this B, but it's not B on the handout. Suppose I took cotangent T plus tangent T over the secant of minus T. How could I simplify that using my rules of thumb? What's the first thing I should do? Well, again, I start with algebra. What's an algebra step? Well, wait a minute. There was a rule 0 that said if you don't have all the same angle, you should try to get the same angle. I have T and I have angle minus T. So what do? I immediately use the even identity. I rewrite this as cotangent T plus tangent T over secant of minus T is the same as secant plus T. I'll just change it. By rule 0, I get one angle. It's using a trig function. I guess you could call it rule 3, 2 also. But we'll say get one angle. Usually you won't have to do that. There's very few problems in here until next section that you need to get one angle first. It's just like this one problem. But still, let's do it. All right, now what do? I go to rule 1. I say algebra. Is there anything I can cancel? Not really. Not the way it's written. Are there any quotients to come on? Not really. There's nothing to multiply out. So I'll skip over algebra. I'll say, is there an identity? And I'll look at those. That doesn't look like any of those. If it was squares, maybe I could do something. So I'll go to rule 3. I'm stuck again. if I replace this in terms of sine and cosine, then instead of 3 different trig functions, I'll only have 2. Maybe that'll make it easier. Initially, it makes it look harder. I'll replace cotangent with cosine over sine. I'll replace tangent with sine over cosine. And replace secant with 1 over cosine. That doesn't look better. That looks harder. So what do I do with that? And I guess I should say here, this is rule 3. I guess it's 3. Write sine and cosine only. All right. Now what I do is I go back to rule 1. I say, wait a minute, there's compound quotients. Maybe I can get rid of those. So eliminate compound quotients. How do I do that here? This is an algebra question, right? I just made my compound quotients. I guess I could put it back, but that's not where I want to go, right? When I have multiple quotients here, I can multiply the top and bottom by the least common multiple of the denominators, they say. The smallest thing I can make that includes sine and cosine, the 2 different kinds of denominators. So I'll multiply top and bottom by sine t cosine t. So sine t cosine t times the top, cosine over sine, plus sine over cosine, over sine cosine times 1 over cosine. There we go. I multiply the top and bottom by the same thing. It doesn't change the quotients. But now see how I eliminate the compound quotients, right? You have to think about it. Maybe you want another step in the middle here. All right. I'll put one more step. I would not usually write this step once I'm used to it, but the first time we should probably do it. How do you multiply this out? This is tricky algebra here, right? You've got this one is some number a, right? Once you plug t in, this becomes a number a, times this one becomes a number b once you plug t in, divide. This one becomes a c. You distribute, right? This times this plus this times this is how you multiply it out. So sine cosine times cosine over sine. That's a times b. And then I take this times this and add it to it. Sine cosine times sine over cosine. So it looks like it's making it worse for a while. Now on the bottom, I'm luckier because the cosine and the 1 over cosine cancel. And I just have sine. Now here's why you can usually skip this step, is because you can kind of see this beforehand. Now I notice this sine cancels this sine on the bottom, and this cosine cancels this cosine on the bottom, so I have cosine times cosine is cosine squared. Sine times sine is sine squared. All over sine. And this is just, here is just distributive property. You multiply it out. So multiply out, let's say, just to put an easy term. Multiply out. Again, it's an algebra step. It's step 1. Now you cancel common factors. Again, it's an algebra step 1. Right? So I mean, these are both the same step, is what I'm saying. You can do all your algebra at once. Now, I don't see any more algebra to do. All the quotients are combined. There's no more compound quotients, but I do see something that looks familiar. What's the top? Yeah, it's the Pythagorean identity. It looks like, remember, sine squared plus cosine squared equals 1. Well, you can add them in the other order. It's the same thing. Cosine squared plus sine squared is equal to 1. Just add it in the other order over sine t. And now what? So this is trig identity. Whenever you see cosine squared plus sine squared, usually just write 1. Normally it's what simplifies it. Now I've got a reciprocal identity. That's why you have the table sitting here. 1 over sine is now cosecant. There it is. That whole thing, I know the graph immediately. It's just cosecant. And it's hard to recognize those things, but this comes up a lot in practice. Moreover, another thing that comes out of it, suppose you have an equation with lots of trig functions in it. What happens is it turns out you use these same rules of thumb and add one more thing. You try and work both equations towards the middle, and you can prove the validity of trigonometric equations doing this. I guess I better erase these, huh? Any questions on that one? That one's kind of complicated. It always looks easy in the board, and then you, oops, shoot, I just pushed the wrong thing. Hold on. And then you go do it at home, and it's just hard to guess which one to apply. All right, so here's time for this one. Yeah. Here's another one. Let me do 1 plus tangent squared over cosecant squared plus sine squared. I'm going to have to get rid of this. We don't need these so much. Plus 1 over secant squared. How about that? How can I simplify that? There are some things you can try, actually. I mean, you could use algebra to try and put these over a common denominator, and that would probably work. And like I say, I should add some to what I said before. In fact, if you get it to work and it takes longer than I take in class, that's fine. What I want you to do is prove each one of these things on the test. Simplify this down as far as you can. If you have to take more steps than I do, that's fine. I won't mark anything off for taking more steps. All right. And actually, if you put these over common denominator, you could probably simplify this thing that way. But let's do something a little easier instead. I think this works better. If I don't apply any algebra at this step to put them over a common denominator, then I go to the next one that says apply a trig identity. Do I see a trig identity? I do actually. This is where sometimes it takes you a lot longer because I recognize 1 plus tangent squared. Identity over here is just secant squared. I'm going to take this and just replace it immediately. Whenever you see in an equation like 1 minus cosine squared, what do I replace that with?
Good question.
Yeah.
Is the T on there supposed to be theta?
Oh, yeah. Yeah, theta. Thank you.
Yeah.
Make them all the same. It might be T on there. I probably miscopied the letter. If you ever see 1 plus tangent squared, that's the direct identity, right? It says directly you have secant squared. That was the second Pythagorean identity, second theorem we wrote over there. But if I see 1 minus cosine squared, I should also recognize an identity since I know that sine squared plus cosine squared equals 1. I can subtract cosine squared from each side and notice that sine squared is 1 minus cosine squared. So whenever I see 1 minus a square of a function, I'm thinking maybe a trig identity. I could replace this wherever I see it with sine squared, and that will simplify it too. So whenever you see the square of a function added or subtracted from another square from 1, think it might be one of those Pythagorean identities. 1 plus or minus a trig function squared. This one would become sine squared, right? 1 minus cosine squared is sine squared from the Pythagorean identity. This one I want 1 plus tangent squared gives secant squared. So you're kind of looking for that with your eyes. 1 plus or minus a trig function squared as you go. And here I see one at secant squared immediately by the trig identity. If you don't see that, because like I say, when I was first doing these, I didn't recognize this one. If you went through and rewrote this all in terms of sine and cosine, guess what would happen out of this? When you simplified it, it would become a sine squared plus cosine squared, you'd probably recognize it. So turning into sines and cosines makes it easier to recognize the identities you know, I think. All right, so I'll try a trig identity there. This is step 2. Identity applied. And then plus sine squared. And how can I rewrite 1 over secant squared? That has a trig identity too. What is this?
Cosine squared?
Yeah. 1 over secant theta, we recall, is cosine theta. That's a reciprocal identity. So if I square this, 1 squared over secant squared is 1 over secant squared, I'll just get the square of this. So this one is cosine squared. apply this trig identity. So I'll apply two trig identities, one to this one here and one to this one here. Now I've simplified it a lot. I got rid of this quotient, I got rid of this sum into a single trig function. What can I do with that? I recycle if you want. I go back up to I either write in terms of sine and cosine only, which is an option, but I think it'll take longer. But you go through that list, then you recycle to the top and you say, is there an algebra? Well, there's nothing to cancel there, really. I could combine these and that would probably work. But if I go to the trig identities one next, that's equal to 1. So what I have now is I'll apply two trig identity again. And say this is secant squared over cosecant squared plus 1. How about that? Oh, it's already over. Okay. Now what can I do with this? That looks kind of hard. Maybe that's as far as it goes, but what you do is you say, well, I don't see anything to cancel here in algebra, and I don't see any more trig identities to apply. I could use algebra and put this over a common denominator, right? This is secant squared plus cosecant squared all over cosecant squared, but I don't see an immediate application of that. So that would probably work with more steps again. But instead, I'm going to do this. I'm going to go to step 3 and say, I feel kind of stuck. I'm going to rewrite this all in terms of sine and cosine. I'll write secant squared is 1 over cosine squared, right? Secant is 1 over cosine. Secant squared is 1 over cosine squared. Similarly here, cosecant is 1 over sine, so cosecant squared is 1 over sine squared. I've got that. Now, algebra, right? So this is 3 using the trig identity. Sorry, 3 using sine and cosine only. That's often a big help on these. Now I'll go back to recycle to step 1 and apply algebra because I've got a compound quotient, right? Top times bottom over middle times middle gives me sine squared over cosine squared plus 1. What's that?
Tangent squared.
Yeah, tangent squared, right? Sine over cosine is tangent. Sine squared over cosine squared is tangent squared. And what's that? Tangent squared plus 1.
Secant squared.
Yeah, I could just write that as secant squared. So the whole thing, that big mess over there was just a fancy expression for secant squared. But this happens a lot because of these nice trig relations. Now what can happen sometimes is you think of doing this and that doesn't look any easier. But there are lots of alternate routes. Another alternate route, if you have trouble recognizing 1 plus tangent squared, is from here to use algebra to put them over a common denominator, right? I write this one as cosine squared over cosine squared. So I'm just showing you what can happen in your homework. It might take a couple extra steps, but you get it, right? So from here, go to here, put them over a common denominator. Now it's sine squared plus cosine squared over cosine squared. 1 on the top. So it's 1 over cosine squared. And now I get to the same spot, just in more steps. And I recognize it's secant squared. So there's lots of ways to do this. 2 steps or 1, 2, 3, 4 steps. Come up with the same answer. So I'll scratch this out. This is just an alternate. All right. Any questions on all those then? You want to look at? Try some of these. On the trig identities, you just want to do all of them. That was 6.3, 1 to 11. Sorry, there's inverse trig functions with that section. And then this one, same thing, all of them, 7.1, 1 through 4 on the UCO supplement. I think this is a nice problem set for getting this. And we did a number of them, so if you get stuck, you might see them on the list. All right. Well, next time what we'll do is we'll introduce some new trig identities. And the object is to just do exactly the same thing, but with more identities we can apply. And what's more, we'll start solving some equations too. Right? Thank you. See you next time.